Wonderful. Good morning, everyone from Washington, D.C., and welcome to the first session of our Ambassadors Water Experts Program, or AWEP, with Belize. My name is Elizabeth Goffey, and I'm a project manager with the U.S. Department of the Interior's International Technical Assistance Program, in partnership with the U.S. Embassy in Belize and the U.S. State Department's Bureau of Oceans and International Environmental and Scientific Affairs. We're so excited to be working with Belize on the important issue of groundwater. Sustainable groundwater management is an integral part of water security. Over the past several months, the AWEP team has worked closely with our colleagues at the National Hydrological Service to put together a program that will support the government of Belize in reaching its water security goals. Today, our groundwater experts will provide an overview of the basic tenets of geology and hydrogeology, laying the foundation for more in-depth technical information to follow in the remaining two sessions. We hope this will be an interactive session with plenty of discussion, so I encourage everyone, if available, to go ahead and put your name and organization in the chat. As a reminder, today's session is scheduled for 90 minutes. There will be extra time reserved at the end for questions, and for folks who are unable to stay for the full time, we will be sending out the slides as well as a recording link, and feel free to put any questions you have in the chat box as well. If you have any technical difficulties, please send me, again, Elizabeth Goffey, a direct message. And without further ado, please join me in welcoming today's expert speakers. And I think Anne is going to kick things off for us.
Well, thank you for being here with us today. It sure says a lot about what you decided to make a priority this morning, and we greatly appreciate it. So Phil Martin and I, Anne Murray, we're both professional geologists. We are a team with Wellspring Water Solutions, and we are thrilled to be here to present the first part of this three-part series to you. So the purpose of the webinar series, just to get you kind of teed up in understanding the whole picture, it's to strengthen your understanding of hydrogeology and groundwater in order to support effective water resource management in Belize. That's a tall order. We get that. It's a tall order in many countries. Today, we'll tie the fundamental concepts of geology and hydrogeology to Northern Belize Corzal Basin, which is our study area. In webinar 2, we'll be getting more in depth with aquifer characteristics, water quality, and water balance.
Yes, all right.
And in the final webinar series, we're going to kind of pull all of that together and talk about something that's very actionable: groundwater assessment and monitoring. Now, mind you, there's a lot of information that we'll be presenting, and know that we'll be touching on many of these concepts multiple times. So if you don't get it the first time, you know what, there'll be other opportunities. And also note that there's resources that are indicated on each one of the slides, and there's more resources that we can supply if you're interested in diving deeper into specific subjects. So I wanted to say that the overall state of Belize water resources, to our understanding, especially groundwater, is not well understood, and this makes informed decisions about development of Belize and implementing national water policy difficult, if not impossible. Groundwater is a main source of water in many areas of Belize for irrigation and drinking water. And like so many places in the world, expanding agriculture and industry in response to population growth is stressing water sources out and degrading the environment. And climate change is making it even more exacerbated. In Belize, it's not so much that there's this water quantity problem, because there is ample water. It's that water may not be available all times of the year, like in the dry season, where things get kind of droughty. And at other times, there's too much water that provides flooding. You well know this because you're headed into your rainy season. So the challenge is to find a way to effectively manage your water resources, to smooth out those extremes and ensure a sustainable water supply. So with that said, we thought it would be kind of fun to put together a poll, and with Elizabeth's help, we're going to start our series off. So don't be afeared. It's 10 questions. It's a fun challenge, and the idea is you can complete it. We'll complete it before and after the presentation. They're the same questions, and they're based on the contents of this webinar. So they're not rogue questions about things that have nothing to do with this. So we recognize that there are varying levels of experience, so don't be daunted by either the material in the webinars or the questions. It's just supposed to be fun. And we'll present the results of the poll at the very end. So with that, I'm going to unshare my screen and send it back over to Elizabeth.
Thanks
And
so much, Anne.
so how do I do that?
Should be a red X stop share button. So I'm not actually sure you would need to. I think the poll will overlay on top of the presentation.
Oh, okay. Why don't you try it?
All right. At this point, you should now see the session 1 pre-survey questions.
And actually call the number back. It doesn't get anywhere.
As a general reminder, please try to stay on mute for the quality of the recording if you're not speaking or asking questions. If I mute you, I do not mean any harm.
I'd also say don't overthink the questions. Just take a good stab at it. There's 10 questions. Well, let's give it I don't know, Liz, what do you think? 5, 6, 7 minutes?
Yeah, I think that sounds reasonable. And if we get a good number of responses before then, we can always wrap it up a little bit early. So it's about 10:40 right now. So I'll say like 10:43-ish, we'll end the poll. This is your 30-second warning. Be like a standardized test proctor. Okay, we're gonna go ahead and end the poll. Thank you so much for your participation. I'm gonna quickly download the results so that I have them for our reference later. And then I will turn it back over to Anne to continue with today's session.
Well, great. Well, thanks for participating in that. I hope it wasn't stressful, and it wasn't meant to be. So now you know what it's going to look like. So I'm actually going to flip over here so you can get, kind of an overview of what we're going to be talking about today in just a short snippets here. So you can see this is what we're going to cover today, and I'm going to be handing this over to Phil to tee us off with the first segment, which is the geology, hydrogeology, and groundwater systems.
Thank you so much, Anne, and thank you all for joining us today. We're very pleased to be here. And Anne, thank you for that wonderful introduction. That was really great remarks that you made. I think that really sums up why we're here. So, as Anne said, we're going to be presenting a lot of material today. We'll be going through some of this fairly quickly, so hopefully it won't be too foreign. And for those of you who are familiar with some of this, it won't seem too basic. We're trying to cover all our bases here. So we're going to start with the Earth history and the geologic timescale. So as you can see here, the history of the Earth goes back approximately 4.54 billion years. The GA stands for billion. And it's obviously an extremely long period of time. Now, this is based on radiometric dating, and these dates are considered to be within 2% of being truly accurate. So the Earth is pretty darn old. Now, as per the figure that's here, you'll see going across the top, we have a number of different categories here that they've broken it out into. And so it's going down into finer and finer breakouts during the different time periods. Many of these are based upon fossil records and tectonic events and significant events in the Earth history. The eons we don't generally worry about too much. The eras, it's the big three. We have the Paleozoic, which means old life, the Mesozoic, which is middle life, and the Cenozoic, which would be, of course, new life. And the Mesozoic in particular, you're probably familiar with at least one of the terms there, the Jurassic, that being made famous by Jurassic Park, such a fun movie. Looking ahead to the more detailed breakout and coming closer to this period where we are today, is the Holocene. And that's the period following the last advance of the major ice sheets in the North American regime. It's approximately 11,800 years. And during that period, an awful lot happened with regard to the aquifer that you're going to be dealing with your assessment and monitoring in northern Belize. And this is something that you will become more and more familiar with. And these characteristics of the aquifer that were formed during the Holocene are going to make your life a little bit more difficult and certainly more interesting than would be the case with certain other types of rocks. I do want to point out also that the Holocene, which represents just a tiny portion of the total age of the Earth, if this scale were put in to accurate scale with the 4.5 billion years at the bottom, and looking at this little short 12,000 year span, that represents only about 0.0003% of the age of the Earth. And if it were scaled properly, it would be just a tiny thin line at the top of this whole column. So real quickly about the fossil on the left and the artist's rendition of that fossil on the right. This is a little critter known as Opabina. It was something that lived during the Middle Cambrian period, so way, way back down at the bottom of the periods in the middle. This little guy was around at a time when Mother Nature was trying out all different types of things with respect to life forms. This guy had 5 eyes, a backwards facing mouth, and a little proboscis that came out and apparently fed it into the mouth. It's easy to say that if evolution had taken a different path, maybe we'd all be walking around with 5 eyes. Also note that on this time scale in the periods in the middle, the Neogene and the Paleogene were previously known collectively as the Tertiary period. They changed this recently for whatever reason, I'm not entirely sure, but it has been changed, and it's something you may run into, the term tertiary, in your older review of maps and things like that. If we can go on to the next one, Ann. So the principles of geology. These are good to be aware of. They're not anything that's going to be super important with respect to the work you're going to be doing in the Yucatan, but it's something that you should know about. And we have 5 principal ones here, and then there's one little extra cookie that we added on to the end here because it is important with respect to Belize. So uniformitarianism. What this states is that the geologic processes that we observe today have not changed over time, and thus we can infer the past by observing the present. Second one, original horizontality, states that geologic deposits were initially laid down horizontally, and thus if you now encounter them being tilted or folded, some other forces have acted on them over time. I don't think you're going to see too much of this in the work with the Yucatan, in that it's going to be mainly still flat-lying rocks, but it's another good thing to know about. Superposition. This states that within a sequence of rock layers, the oldest rocks will be at the bottom and the youngest at the top. Seems fairly obvious, but in certain instances, the rock sequence may have been disturbed and, for example, totally turned over. So you would find young rocks below old rocks. And if you didn't have familiarity with the law of superposition, you might think that that was normal and okay. It is obviously true that something has happened there. And cross-cutting relationships, the graphic on the right gives a whole bunch of these types of things. Taking, for example, down at the lower left, it says cross-cutting. You see that intrusion labeled R. It must be younger than all the formations labeled A through the lower part of Q, but it's older than the upper portion of Q and S and T. And also note that A through G are truncated horizontally by J. So these things happen all the time in more intense structural settings. You'll see these kind of things, and it makes it sometimes very difficult to understand exactly what's going on. I think the only thing you're going to see here is what's the next principle, and that's the principle of unconformities. And this is that they're simply gaps or missing data in the rock record. These gaps could indicate a variety of processes such as erosion or the fact that the rocks never were there in the first place. They simply weren't deposited until some other formation came in and were deposited much later. We have 3 types: the angular unconformity, which you can kind of see at the bottom of the graphic on the right. All those rocks are tilted pretty significantly. We have a disconformity, which is a rock orientation that's similar, in other words, flat, but you have a large time gap or an unconformity existing between the layers. And then finally, nonconformity. This would be rocks of different type, for example, metamorphic rocks, igneous rocks, overlying flat-lying sedimentary rocks. So all of these are exhibited in that graphic on the right. And as you'll see later in slide 12, there are significant unconformities in the limestones that comprise the Yucatan aquifer. Now, the last one that we have here is extraterrestrial. It's not truly a principle, but it's a major factor in the evolution of the Earth. The graphic on the left is from a NASA topographic scan of the Yucatan. And this is showing something here that represents an event that changed the history of life on our planet. It was an asteroid or comet impact that marked the end of the dinosaurs and the end of the Cretaceous about 66 million years ago. The Chicxulub impact, as it's known, was a very significant event, and it was just offshore to the north of the northern boundary there of the Yucatan platform. You'll note on that diagram, and Ann, maybe you can point it out, there is a subtle ring that shows up, and this is a topographic map from NASA. And that little topographic difference is not much, but it was picked up by the NASA satellites. And there's also a ring of cenotes that parallels that. Well, this is a reflection of the impact crater from 66 million years ago. I'll point out that none of the limestone rocks that form the peninsula now, or that are what we see in the peninsula, existed at the time of that impact. But it was such a major event, with such tremendous energy, that it still has left a reflection of it in the rocks that have been deposited since then. So if we can go to the next one, Ann.
Mhm.
So Chicxulub, which means tail of the devil from the Mayan word, there is a little settlement called Chicxulub up near where the impact occurred. And it's interesting to point out, tail of the devil, it's an interesting term because it was certainly a devil of a time for anything that was alive back when this event happened. This is at the end of the Cretaceous and the end of the Mesozoic, and it ended the time of the dinosaurs. So this impact blasted out material radially for over 180 kilometers, or about 100 miles. And this material has been found in boreholes in a number of locations in northern Belize. And just quickly with the graphics, and this is a great find, the graphic on the upper left shows the asteroid approaching the Earth. The upper right is an unfortunate dinosaur about to meet his maker. In the middle is a representation of what the landforms looked like at the time the impact occurred. As you can see from the outline, pretty much all of the Yucatan Peninsula that we recognize now wasn't there. There was, however, that large green area in the middle that represents really the core of the Maya Mountains that you are, I'm sure, familiar with in Belize. Down on the lower left is a graphic showing the height of the waves that were generated by as a tsunami after the impact. And one number that's down there at the bottom is 269 meters of waves. This was a just incredibly violent event. And then over on the right is just again an adaptation of where the crater was centered, just offshore of that little village of Chicxulub. So if we could go to the next one, Ian. So we want to look at some basic rock types here. And this is again, very basic geology. We have two general categories, the unconsolidated and the consolidated. The unconsolidated deposits, they're not really a rock type because they're unconsolidated. They're not cemented together. And this is something that's referred to as being indurated when a rock is cemented and is actually a consolidated formation. So we have in the unconsolidated area, we've got things like alluvium and dunes. It could be beach sands, deltas, clays, or highly weathered bedrock that's just loose material that is eroded away. In that graphic that's right to the right of our consolidated and unconsolidated listings, you do see a section of a vertical section of sand and clay, sand and gravel, and then clay. And these are all unconsolidated deposits that have been deposited in a very interesting section. Then we move to the consolidated rocks. And this is where we have our big three, the sedimentary, the igneous, and the metamorphic rocks. Now the sedimentary rocks, this would include sandstones, siltstones, shales, and limestones. And in particular, limestones are the ones that you're going to be dealing with most of the work that you're going to be doing in monitoring and assessment in northern Belize. It's one of the most challenging to characterize, especially when it is karstic in nature. And we're talking about that a lot more in the rest of this webinar and the subsequent ones, which means exhibiting solution features such as caverns and sinkholes, cenotes, and dolines. Now you see in the upper right in the middle, there's a bunch of layered sedimentary rocks. It's possible that one or two of those thinner layers might have been representing the limestone. More than likely, there are shales, dark rocks, and then some sandstones and siltstones in there. But interesting coloring showing off the fact that these were layered rocks. The next big one is the igneous rocks, which can be of two types. You have intrusive igneous rocks, which means basically rocks that were never exposed at the surface while they were forming. And this is where you have a magma chamber, such as in the graphic on the lower right, that is down at some depth of burial. The rock has been melted, and now it's going to be recooling and consolidating in place. Now, these are typically referred to as a generic term of granites. I will warn you that there's many different types of granites based on their chemical makeup. So it's just a catch-all phrase for those types of rocks, the intrusives that are that consolidated in place in deep burial. The other type of igneous rocks are the extrusive, which means coming to the surface and coming out as either flows in a more passive sense, kind of what happens in Hawaii with some of the volcanoes there, or an explosive extrusive events like a typical volcano that we think of, as in that little graphic where we've got the smoking volcano there. These are of many different types. Both extrusive and intrusive rocks can have many different forms of chemical makeup and physical character, but those are the two big examples. Down in the lower left are some photographs of some of the different types. You can see in the very lower left of that where the fingers are, that's basically a pumice type of rock. That would be an extrusive one that was blown out and subject to falling through the air. It already contains vesicles, they're called, those little pores. But then you've got more massive examples of intrusive rocks that have been brought to the surface through erosion and exposed, like in the upper left of that particular graphic. Finally, we have what are referred to as the metamorphic rocks. And these are rocks of any original source, either sedimentary or igneous, that have been subjected to intense heat and pressure and have become thermally and chemically altered. And some examples of these would be a sandstone that has been altered into a quartzite, or a limestone becoming marble, or shales that become slates, and granites that could become a gneiss or a schist. And there's a great picture of a schist up in the upper right, where you can see it was once a banded type of rock, potentially even a sedimentary rock layer that has been just squeezed and turned into toothpaste at some point, apparently, where it became plastic in nature, and it's been really very significantly mixed up. So the rock cycle is what's pictured at the bottom. I don't have time to go through this in detail, but I encourage you to go ahead and look at this later on when you have access to the slide deck. It gives the full picture. Go counterclockwise through this, starting with the magma, and work your way around, and it gives all the different things that have to happen. And this process, by the way, would be something that goes on for millions of years to go through the whole cycle once. So with that, we're going to go to the next slide, and this will be a handoff to Ann.
All right, I have successfully unmuted myself. All right. So the geology of Belize. So we just looked at a real big picture of geology and some of its components, but let's hone in on what's going on with Belize. Okay, let's do that. Let me just see if I can click through this. So geologists love maps, and the reason why we love maps is because these maps show different perspectives. So structural geology, if you take away nothing else, is that Belize is really shaped by plate tectonics and the extensive amount of faulting that occurred in the area. So if you recall plate tectonics, there's large tectonic plates that sit on the Earth's lithosphere and move around slowly. And this is evidenced by continental drift, like that graphic that Phil showed at the beginning with the banding of the different movements of the plates. So this is evidenced by continental drift, where you can actually see plates, the continents riding on the plates and moving around. And it's a result of seafloor spreading. So in figures 1 and 2, you can see that Belize is located just north of the Keyman Trough. Well, this is extremely important. This is a complex transform fault. It's a pull-apart basin, and it contains a spreading ridge. So what's important about that? It marks a tectonic boundary between the North American plate and the Caribbean plate. So there's a slow eastward drift of the Caribbean plate, and that has resulted in giving the primary structurally controlled features of Belize, like the Maya Mountains, the offshore atolls surrounded by deep water, and the location of the coral barrier reef. So the mainland of Belize can be divided into 3 geological provinces. So if you could see on the figure 3 there, in the north is the Corizal Basin, in the south is the Belize Basin, and in the south central is the Maya Block. So the Corizal Basin is an extension of the Yucatan platform, and it's stratigraphically part of the North Piton Basin of Guatemala. What you can take away from this is that there's numerous large fault systems that have impacted the current geologic conditions in Belize. So I connected a red arrow between figure 3 and 2 just to show the Corizal Basin as being part of that lower portion of the Yucatan platform. Okay, more maps. Gotta love it. These ones are colorful. So again, they present a wide variety of geologic information in different ways. And so we can learn from these because they are our key resources. And they come from extensive field work and research. So the map on the left shows landscape terrain. It's showing the younger sediment deposits in yellow, non-carbonate deposits in orange, including the Maya Mountains and the southern Belize Basin area. And in the carbonate series is shown in blue, showing relative depths. The lighter the color, the shallower the deposit. The map on the right shows the age and type of rocks making up Belize. So the oldest Paleozoic era igneous, metamorphic, and sedimentary rocks that make up the Maya Mountains are in red, and it represents a faulted block of Mayan crust. The younger Mesozoic era Cretaceous limestones in blue flank the Maya Mountains to the west. The youngest Cenozoic era clastic sediments are shown in lime green. They were formed as a result of erosion. The youngest limestones are indicated in mint green and light blue, and they're formed on a more structurally stable Yucatan carbonate platform. In general, if you're going to characterize the basins, the Corzal Basin could be described as carbonate dominated, while the Belize Basin sees more of a clastic input in the large part of that section. So these maps demonstrate an understanding and an importance to understanding subsurface formations that directly inform our understanding of groundwater resources. Now, not to be dismissed, the map in the middle is a really spectacular piece of work, and it's a collaboration between the government of Belize and the United Nations Development Program, and it's considered the official geology map of Belize. There's a tremendous amount of information here that includes superficial geology and faults, the subsurface cross-section, the stratigraphic column, detailed descriptions of formation, but the blocks of information are not really readable at this scale. But I know where you live, and I'm kind of sure that you can get to the Geology and Petroleum Department within the Ministry of Economic Development to actually see this original map and use it as a reference, because it is really a good piece of work. Let's focus a little bit closer in. So this is the Northern Belize Study Area in the Corzal Basin. What I wanted to tell you about here is that the Corzal Basin shown on the left is an extension of the Yucatan platform, as we've already said, and it's comprised of these thick marine carbonate sequences deposited over the last 50 million years or so. The extent of the Yucatan limestone platform is shown on the right, and it's outlined in red. So it's situated primarily in Mexico and includes part of Guatemala and Belize. The background shading indicates the topographic elevation. So where you see white, that's the highest elevation, and green indicates the more low-lying areas. The southern extent of the platform is defined by an anticlinal arch and the associated fault zone. I've got a little inset there because it is kind of interesting, and the faulting is very extensive. What's interesting about this southern extent of the Yucatan Peninsula, it lines up quite nicely with the fault zone where the Belize River follows. And I'll just point that out. So here's Belize City, and here's the Belize River. So what else is noteworthy here is that the Yucatan Peninsula has a karst aquifer that's associated with it, and this is a transboundary resource. It's a primary source of water for the peninsula. So there's major cavities and conduits that have developed as part of a karst aquifer evolvement, and it includes extensive cave systems and cenotes formed by the dissolution of carbonates, limestones and dolomites in particular. Let's look at this from a different standpoint. These are stratigraphic columns. On the left, you have your reference geologic ages. Next to that is the strat column for Guatemala, and then 2 for Belize, the middle one being the Corzal Basin, and then to the right is the Belize Basin. So just from a color standpoint, you can see that there's some similarities and differences. And these are a result of different structural events and depositional environments. There's some similarities, some differences. Okay, so we can follow that in Belize, these are more similar than Guatemala, for instance, but we do see that there's some similarities in the limestone and some of the shale that's been laid down. I wanted to refer back to something that Phil had talked about, which is an unconformity. And these show up as those squiggly lines and black and white up and down lines. So as Phil said, this is a gap in the geologic record where there's actually a missing sequence of overlying younger rocks. And it signifies that there may be a period of non-deposition, or there may be an extensive period of erosion. So what happens here is this, if it's an erosional surface, there's hundreds of millions of years this could have been eroding. And what it does is it results in rocks of very dissimilar ages and composition in vertical contact with one another. Lastly, in this segment, I wanted to talk about geomorphology. So what is geomorphology? That's the study of landforms and landform evolution. So this is the forces acting out and near the surface on the geology. So this is really telling. The Corizal Basin is comprised of 3 distinct landform units. To the east, the coastal plain with swamps and floodplains of a younger quaternary age. The central plains have that gentle topography and lakes that were created by subterranean karsting and overlain by lower and upper tertiary carbonates and clays. And then there's a western expanse of hills ranging in topography or elevation levels of 100 to 250 meters, and have associated rivers and floodplains. Again, why is this important? What we read at the surface helps us to understand more about groundwater and its vulnerabilities, for that matter. So it gives us more clues. That I'm going to turn it over to Phil to talk about carbonate rocks.
Okay, thank you, Anne. Well done. So we've been talking a lot about carbonate rocks. Just exactly what the heck are they? Well, generally described as sedimentary deposits that form in marine environments, and oftentimes a shallow, warm marine environment, like a shallow, warm sea, where marine life is abundant and you have coral reefs, shell-forming animals, etc. So this is where limestone and the general carbonate rocks come from. So there's several types of carbonate rocks, and I'm talking here about sort of the general categories. We have limestone, which you've certainly heard us talk about, which is predominantly calcite, which is calcium carbonate. And it's oftentimes referred to as pure limestone if it is just solely calcium carbonate. Because if you have anything else added into it, it becomes a little bit different and it changes its character. And there's one real important point in that statement that we'll get to in a minute. So dolomite is another one of the rocks. You may have just noticed that on the stratigraphic column that Anne had just had up. This is where you've got some magnesium coming in and mixing with the calcium. And so you've got calcium magnesium carbonate. And this is limestone where the calcite has been chemically altered via contact with magnesium-rich groundwater. So it changes it. And while it may seem like a minor change, it actually does change the character of that rock. And here's where it's important, is that the pure limestones are very, very susceptible to the solution processes. And we'll be talking about that in a couple slides. The dolomite is less so. So the dolomite's going to be more resistant, but the pure limestones are going to be quite susceptible to that. There is another substance referred to as anhydrite. It's a type of a rock that forms where large volumes of seawater have been subjected to evaporative conditions over long periods of time. And we end up with basically calcium sulfate. And this is another rock that does occur in the Corizal Basin, but usually in thin beds. You're not going to see an awful lot of that in the work that you're doing with the kind of the superficial monitoring and that type of things. Now, as noted, there can be a mix of the mineralogy, both laterally and vertically, and such blending can alter the solution characteristics, as I just mentioned. In other words, the ease of dissolution. And again, just to hammer it in, the pure calcium carbonate, the limestone, is highly susceptible to that. Now, just as a final definition, limestone is usually a biological sedimentary rock, which is an interesting term, I think, forming from the accumulation of shell, coral, algal, fecal, and other organic debris. It can also form simply by chemical sedimentary processes where you may have small particles of silt or even just tiny other pieces of shells and things that are floating in the water column. And there's enough calcium carbonate in the water, and it just precipitates onto those. They settle to the bottom and become a deposit that's not consolidated yet, but a pre-limestone, if you will. So just going down quickly, as it says on the left here, those are the main points. Those deposits settle to the bottom. The compaction and sedimentation process takes over. If it's exposed and allowed to be impacted by precipitation, those solution features will begin to appear. And this is pretty much the typical description of the Yucatan limestone aquifer. So if we can go ahead, Ann. So how did this all get here? As we noted in the geologic time scale, we go way back with the start of the Paleozoic as far as where the Yucatan platform comes from. And before we get down to the listing on the left, I do want to point out the graphic that what we see above the water surface, which is what we're all familiar with as the Yucatan Peninsula, is just a tiny portion of the actual Yucatan platform. It extends out under the water for a lot of miles, a lot of kilometers. And it goes down, as you can see, begins to get steeply dropping off into the deep sea basins as you get into those darker blue contours there. So it's a very large feature. And it started with the deposition and more metamorphosis of sedimentary rocks that were up to 2,400 meters thick. And they're down there a long ways. They're buried at the bottom of that whole column of things that Dan presented in the stratigraphic columns. And then during the early Mesozoic, we have deposition of the Todos Santos Formation red beds. And we mentioned these because they're kind of a distinctive marker. They're shales that have oxidized and they are fairly red. Interestingly, these types of beds show up all over the world in different places and all about in that same time frame in the Triassic. It's an interesting phenomenon that reflects something that was going on in the atmosphere at that time in our Earth's history. And so it becomes a distinctive marker that can help with correlation of the various geologic units that are encountered in the strat columns. Then during the Cretaceous, we had a whole series of marine transgressions and regressions when shallow seas moved in, covered an area, deposited some dolomites, moved back out, came back in again, deposited some more, and built up about 1,300 meters of dolomites. And then following that, we get into the Tertiary, or using the new terms, the Paleogene and Neogene, an additional 1,000 meters or so of pure limestones, and here again, differentiating from the dolomite, no magnesium in this rock, was deposited in a number of stages. And so during the Oligocene, the platform continued to uplift. And then during the Pleistocene, we had the effect of sea level rises and dropping and rising and dropping. And that's where you started getting the open caves, the solution features starting to be formed. And this went on over a million years of time during the Pleistocene. And then we get into the Holocene, where we are at the end of right now. So if we can move on there to the next one. We look at the historic sea levels, and this is pretty fascinating. During the Pleistocene, which was about 1.6 million years to roughly that 11,800, 12,000 years ago, there were numerous advances and retreats of the ice sheets in North America. And every time the ice sheets would move forward, a glacial advance, you'd have a big drop in the sea level as all that water was converted into ice. And then conversely, when the glaciers retreated, you had a big rise in the sea level. And this happened over and over and over again. And it was during those times, as those glaciers advanced and built up, it exposed the limestones to rainwater, which resulted in the formation of many of these features that we have, the dolines and caves and sinkholes or cenotes. And to the extent of the cave that's pictured here, and this is from Belize. And this is a cavern that shows you just the scale of these things can achieve, which is almost unbelievable. I mean, you could drive your entire house through this and have lots of room to spare. And these things go on for miles. Some of the longest cave systems in the world exist within the Yucatan platform. And a lot of them have been mapped. A lot of them are flooded, so there's a lot of underground and underwater cave exploration that goes on. But you can see how it changed in the graphic in the middle. The carbonate platform at 20,000 years ago, you can see how far down the sea level was. And then during the Holocene, it came up, it came up, it came up. And then we have our sea level now 125 meters above where it had been. That's a pretty significant change in sea level. And this is when a lot of the things went on with the flooding of the caves and to where they are now. Okay. I was going to say one last point on this. A good example of a real famous solution feature is the Great Blue Hole that's off the coast of Belize. And any of those of you who may be scuba divers may have had the privilege of diving in the Great Blue Hole. It's an amazing thing to see. We can go to the next one, Ian. So before we get to all the features that are on this graphic, just want to ask the question and then answer it. So how do the solution features form? How does limestone that's basically solid and massive limestone turn into this kind of Swiss cheese thing that we see here? Well, if we start with the pure limestone, the calcium carbonate, if we add water and carbon dioxide to it, which is what's going to happen when it's exposed to precipitation, it produces what's called carbonic acid, and it will very readily start to dissolve the limestone, again, especially if it's very, very pure. So if you look at that graphic here, you can see there's all these places where we've got the caves and the various different things that are going on. You've got a stream disappearing underground, all these little sinkholes, and there would be cenotes that actually do penetrate down to a water table, things of that nature. And this is, in fact, a good representation of what it can be encountered out there. Now, obviously, some of this stuff is much deeper, but still, it definitely looks like this in cross section. And it is a very difficult thing to characterize because these things go off in all different directions, and you can have vertical conduits and lateral conduits and all of the above. And a groundwater table at some point here in this graphic, it shows it being down quite low, and some of the caves above are open and not flooded. But typically in the Yucatan, an awful lot of them are flooded. So once you've got this stuff going on and the uplift that occurred in the Oligocene, you get all kinds of solution activity going on through all these different advances and regressions of the glaciers and the sea levels going up and down. And this is exactly what we get. So if we can go on to the next one. We're going to take a look here at some of the flow systems that can be encountered in karst limestone. I think it's safe to say that you're going to encounter all of these in your work in the Yucatan Peninsula and the northern end of Belize and the Corazal Basin. The diffuse flow that you see here is simply the pathways that allow for precipitation to infiltrate down into the ground, into the limestone, and to carry on additional solution erosion of that limestone and to create new passages. The diffuse flow usually happens where we've got a weathered surface to begin with, which is what you'd expect where that limestone is right up at ground surface. That's where you will have the most erosion, if you will, and breakdown of the limestones from the acid that's formed from precipitation. So the diffuse is the infiltration of the precipitation waters, and that is pretty much the sole source of freshwater recharge to the aquifer, with the exception of some river leakage that can go on, especially if you have a sinking stream, which is noted in the upper right of this graphic. That can happen where you lose some of your stream flow down into the limestone. The point flow is basically a more confined or more concentrated vertical flow that's going to just drop water directly down into deeper layers. And the same with the vertical, that can be much the same as a point flow, but also can reflect water that's moving in basically two dimensions at one time, going somewhat down and somewhat laterally, and then lateral flow, which is again, just eliminating the vertical flow and just having lateral flow paths. And noticing in this graphic, it has the minimal water table way down below where most of the solution features are. And that's where you'd have in this graphic, a constantly saturated zone. overlying at this point some type of rock that's probably much more resistant to any kind of erosion and forms the base of the karst. So if we can go to the next one, Ann. So the Yucatan limestone, and I'll point out that the middle graphic here is one that I just mentioned, and that's the Great Blue Hole off of Belize. Again, just simply amazing feature. I believe it's on the order of 430 or 40 feet to the bottom of that flooded cenote. So we've been able to find, unable, I should say, to find significant data on the Yucatan limestone in Belize. This is something that Ann mentioned in her opening remarks. Oddly enough, most of the information that we have is available only from the Mexican side of the border. So from that information, however, there's a wealth of data that can be learned and a wealth of information that can be applied to the work that you'll all be doing going forward. So in general, referring to the Yucatan limestone, it is very porous. It is very susceptible to abundant and very dramatic, as you see here, solution features. There are extensive cave systems, as I mentioned, and variable composition. It is primarily the pure limestone throughout the bulk of the Corazal Basin, but there are, as you go vertically, certainly there's dolomites down there. But even going laterally, you will run into some difference in the nature of the limestone in terms of its chemistry. You can pick up some areas where you do have both dolomite and hydrite, the calcium sulfate, as you move away from the center area of the Yucatan platform. So you do run into different things like that. It is highly heterogeneous, and these are terms we'll get to in a minute, heterogeneous versus homogeneous. They're very, very important with the work that you're going to be doing, and very, very important with respect to categorizing these types of rocks. So if we go to the next one, I'm going to do a handoff back to Ann.
Great, thanks, Phil. Thanks for setting that up. So let's shift our attention to rainfall and recharge and aquifer types, and talk a little bit about let's talk about something. This sounds very fundamental, but really this is it. The hydrologic cycles, also called the water cycle, and this describes this continuous movement of water above and below the ground. So recall, there's no new water. So we're literally drinking the same water the dinosaurs drank. So if you follow this cycle, water passes into the atmosphere as water vapor. It collects in the clouds get heavy, it rains. That rain looks like, it could be in solid form or liquid form, depending on where you are geographically. And it hits the ground, it either runs off, surface runoff, or it infiltrates into the soil column and then percolates into the aquifer, eventually discharging back into the sea, and ultimately it returns to the atmosphere through evaporation and transformation from vegetation. There on the right-hand side is a rainfall map, and red does not mean bad. Okay, so the colors are a little bit deceiving. What this does say is there's really quite a range of rainfall from north to south, and in the south there's nearly twice as much precipitation than what is happening in the northern part of Belize. However, saying that, the annual rainfall in northern Belize is significant, somewhere between 55 and 80 inches. As you know, it's seasonally variable, and like Florida, where Phil and I are sitting, that rainy season generally runs from June through November. So you are at the beginning or in the beginning months of your rainy season. So during that rainy season, the wet season, these rain events, there's a significant amount of water that falls to the surface. It exits through runoff, watershed drainage, and then through the rivers and discharged into the ocean. So what does not run off infiltrates again into the soil column and percolates into the aquifer. So the recharge rate to the groundwater aquifer has not really been adequately quantified, but we can surmise a few things. Phil just talked about the carbonate formation and its makeup, and the porous karstic limestone. And these occur in much of the Yucatan Peninsula, including those low-lying areas of the Corozal Basin. These show very high permeabilities and contribute to effective aquifer recharge. So the graphic to the left is describing 3 recharge environments. So the very far left is a hilly area. It's underlain by lower permeability matrix. The transition zone in the middle describes a low-lying area. It's underlain with a high permeability matrix zone. And then the flat area to the coastal side is receiving direct recharge based on its coastal location. So there's a few things I wanted to point out here that are kind of interesting and fundamental. So the freshwater supply for the Yucatan Peninsula is a result of rainfall, right? It infiltrates into these carbonate rocks. That's what fuels and fills the aquifer reservoir. In this slide, you can see that recharge is described as a precipitation less evaporation and transpiration. So evaporation to the atmosphere, transpiration through plants. On the far left, you'll also see ejecta, which was interesting. So these are low permeability clays, and they are a direct result of the Chicxulub asteroid impact that Phil talked about at the beginning. So there was a very big splatter effect throughout that was very regionally extensive. We can also see through this graphic that there's preferential flow paths within the aquifer that are equivalent to the regional and small scale fracture zones and dissolution conduits. This is depicted as cave with arrows. So of note is the freshwater lens that's shown in the transition portion of this graphic. And this is a freshwater lens sitting on top of the saline water. This is infiltrating rainfall, fresh water that is lower density than the underlying seawater. So that fresh water forms lenses that kind of float within the pores of the rock and on top of the salt water. And in between those two water quality different bodies, these characteristic bodies, there's a relatively thin, kind of briny, brackish water transition zone that separates them. And we're going to talk about that later because that's a very delicate balance that can be influenced pretty easily with withdrawal. So lastly, because of this karstic nature of the aquifer, the fresh water tends to drain laterally back into the sea. So it's kind of a conveyor belt mechanism where you have precipitation, recharges, the aquifer, it maintains kind of the thickness of the freshwater lens, and then it directs itself off sea, only to be recharged again with that rainfall. So I want to talk, shifting gears a little bit and talk about what is an aquifer. So there's the definition there. And I think of significance is this is, it's quantities of water to wells and springs. So we're basically mining the water for use, right? And there's a lot of different definitions for the term. They all are pretty much equivalent, pretty general. But in terms of practicality, consideration really has to be given to the cost to extract the water versus the availability of water. So for example, consider a very deep aquifer that can provide a small flow of water. Does the need for the water offset the very high cost to drill and complete the well, and then to put a pump in the well and have the energy to pull the pump, to pull the water out of the well by a pump? So that's an investment. So that's a consideration. On the photo to the right is, I don't think we've seen this graphic before, but this is water flowing freely from a solution feature, limestone formation in Colorado. And it's clear that there's a pretty good flow of water here. Well, in comparison to the solution features in the Yucatan limestone, this is kind of small potatoes. The Yucatan can yield great volumes of water, and they can be stored readily, and they're reasonably accessible. In the middle graphic, you can see that this is an artesian well. It's flowing without the assistance of a pump. So we'll talk a little bit more about that in the coming slides. But so this is just flowing under pressure to the surface, no pump required. That's a pretty good scenario. So So aquifers are generally classified as either unconfined, a water table aquifer, or a confined artesian aquifer. So unconfined aquifers will reach an equilibrium state where the pumping, let's say, so we're mining water, right? So we put a pump in a well, we put it in an unconfined aquifer, and when that pumping is matched by the amount of recharge that is received by the reservoir, the drawdown, the amount of change to the water level reaches an equilibrium state, and that drawdown remains kind of constant. So you have a good balance between input and output. So that's not the case with a confined aquifer, where the storage properties differ really quite greatly, and we'll talk about that a little later in the webinar. So a confined aquifer exists between two confining units, and it's typically recharged where the aquifer matrix is exposed to or located near the surface, and it tends to recharge at a much slower rate in comparison to a direct recharge water table aquifer scenario. Let's look at this at a slightly different angle. So there's a lot going on here, but this is a great way to show the different facets of the confined and unconfined aquifers. And we now have installed a bunch of wells, so we can see how they're reacting. We're not pumping from the wells, but we've installed the wells. So starting at the very far left, here's the recharge area. You can see that there's the water table. It's indicated by that triangle. We can see that, just as I was speaking of, this is where the recharge is received not only to the water table that feeds the water table aquifer, but it also feeds this confined aquifer, okay? So we have the water table, which is the depth below which the ground is saturated, okay? And then we have this dotted line. Well, that's the potentiometric surface. This is an imaginary plane where the fluid will equalize out to, if allowed to flow. All right, let's move forward. Here we have a flowing artesian well. So we follow this down. It's in a confined aquifer zone. All right. Then we'll note that the topography, the elevation of the ground level, is below the potentiometric surface. That allows this water, which is under pressure, to then flow. Its head is now above ground level, so it's actually flowing at above ground surface. In the next scenario, we have a perched water table well. This is a very interesting scenario because it describes a couple of things. One is confining units can be different things. Confining unit could be called an aquitard, which has some limited vertical flow and can be leaky. It could be an aquiclude, which is essentially no vertical flow whatsoever. In the case of a perched aquifer, you could see this confining unit is abbreviated, and that water from the water table has collected and recharged just on top of that feature, and that a well can potentially pull from that water collected on that confined unit, and is known as a perched aquifer. And so that's a very delicate balance in its own right, depending on how extensive this aquifer feature, the confined unit, is, and the amount of recharge. Moving over, we see this is a water table well. It is in this shallower, unconfined water table aquifer system. It's readily recharged from rainfall. The triangles again show the water table, that depth where water is saturated the ground. Next to it is an artesian well. Okay, so we have a flowing artesian well over here, and we have an artesian well here. Difference, this well is the potentiometric surface is well below ground level elevation, still called an artesian well, but it's not flowing under its own steam. All right. What are the other points? I think I wanted to mention, Phil had mentioned homogeneity and heterogeneity, and I think that that's really an important part of our conversation, and we're going to keep coming back to that, because one means things are the same and the other means things are different. And when you have things that are the same. It's a little easier to access that water. It's, in Florida, we have aquifers that are very easy to access, and they're very much the same material. There's not a whole lot of difference. So this would be an example of homogeneity. Heterogeneity, you have differences in the composition of the formation that may or may not be giving to water flow. And you could have both of these types of scenarios in the Yucatan limestone, and that is challenging. All right, with that, I'm going to turn this over to Phil to talk about some of these properties and concepts.
Okay, and this is going to be where we get into some fun, I think. Thank you, Ann. We're going to take a look here at some of the most important aquifer properties and concepts. This is sort of the nuts and bolts mechanics of how groundwater flows and occurs in groundwater situations. So it's important to have a good understanding of how they can impact any attempts at characterizing, developing, and protecting a groundwater resource. So these are fairly important. So we're going to be looking at some that may have some unfamiliarity to you, but hopefully the explanations I have will help sort this all out. So if we can go to the next one, Ann. So first up, we have porosity, specific retention, and specific yield. Now, porosity, I think, probably is a fairly recognizable term here. It's simply the ratio of the volume of a material. In this case, if you look at that upper left square of aquifer material, or cubic, excuse me, of aquifer material, it's how much of that aquifer material is actually open space. And this will occur in some rocks, not in all, but certainly a lot of rocks do have some level of porosity to them. And it's described in the equation there, which is the volume of the voids, the V, capital V, lowercase v, divided by the total volume times 100. And it gives you a porosity as a percent. So that's a pretty straightforward one. But where it starts to get interesting now is what happens if you put water into it. So these voids can store water within the formation, and if they're adequately interconnected, they can allow water to move through the rock and release that water to pumping wells or springs. So the upper right graphic depicts that cube of aquifer material as being totally saturated. So we assume a porosity, say, of 30%. Porosities can range from 0 almost to up to 35 to 40%, even in some extreme cases in an unconsolidated deposit. But here we're assuming, okay, 30%. So that means that the water volume in this 1 cubic foot volume would be 0.3 cubic feet, and the rock volume is going to be 0.70 cubic feet. So that would tend to suggest that, oh, we should be able to get that 0.30 cubic feet of water out of that rock volume. Well, here we run into a little problem because it's generally not all that possible to remove all of the water out of a porous media like this volume of aquifer. And the reason is that, as shown in the lower left diagram here, the grains that are in there that have some spaces between them, because of capillarity and surface tension, they don't want to release all of the water. So some percentage of that water that was in that rock mass, in that volume, is going to be trapped there no matter what you do. Now, normally you would remove the water by drying and then measuring that volume and getting the ratio of the voids ratio, and then also the porosity. But here, because of this capillary retention, you'll never be able to get it all out. And this is a fairly typical situation. So we have what's referred to as specific retention. And in the lower right diagram, you'll see that it's depicting some level of water saturation at the bottom. And so if we assume, based on what we saw on the left, that, okay, we've got 5% capillary retention, then 5% of that volume of water that's in there, which is 0.30 cubic feet times the 0.05, is going to equal 0.015 cubic feet in this example. So that's what's going to be stuck in the rock mass. But what's important here is that the remainder of that, which is the gravity drainage yielding, which you see right at the top of this portion of the graphic, gravity drainage yields the 0.30 times 0.95%, or the 0.285 cubic feet of water per cubic feet of aquifer material. That number is referred to as the specific yield in an unconfined aquifer. And this is the amount that could be drained by gravity. If you were to just simply open the bottom up and let it all drain out except for the specific retention, this is what you'd get. It's referred to as specific yield. It's a very important concept. So if we can move on to the next one, these may not be quite as familiar. Hydraulic conductivity, which is represented by the capital letter K, and transmissivity, which is represented by the capital letter T. Now, before we turn to the graphic here, I just want to point out that both of these reflect how easily water can move through a geologic material, whether it's consolidated or unconsolidated, assuming there are pathways for the water to move and that there's water in storage. In other words, there's a voids ratio. There is some water that's being held in that rock mass. So it is derived from the intrinsic parameter known as permeability. It's an intrinsic property of any rock mass or any substance. But in this case, it's specifically applied to water in itself, hence the name hydraulic conductivity, because there can be a gas permeability, there can be a hydrocarbon permeability. So this is specific to water, and it's good not to get them mixed up. Hydraulic conductivity is measured as a velocity. And so the lower left portion of the graphic that's here gives a good explanation. So hydraulic conductivity is the volume of water that can flow through a unit cross-sectional area, in this case, 1 foot by 1 foot of an aquifer under a hydraulic gradient of 1 foot per 1 foot. In other words, a unit, a very steep gradient. In other words, it's dropping by a foot for each linear foot that you go. And it's given an amount of time. It says usually a day. It depends. It could be in seconds, days, minutes, depending on how high the numbers are. As noted on the right, for the Yucatan aquifer, the literature that I reviewed indicated from 1 × 10⁻⁶ meters per second to a number that I find to be totally unbelievable, and that's 296 meters per second, which is a span of 8 orders of magnitude from the lowest number. That high number does come from a computer calibration, and so I think it is ridiculously high, and I would never rely on that kind of a number. But K values, hydraulic conductivity values for karst aquifers can be strongly related to the measurement scale. If you're looking at a tiny block of it that doesn't have much in the way of solution features going on, you can be very small. If you have a large cavern, it can be enormous. So it really depends on scale, and this is something we'll be talking about more in the future. Now, transmissivity, the best way to think of this is just to look at the graphic and say, okay, if we took that little 1 by 1 foot of aquifer material by which we derived our hydraulic conductivity, what if we stack it up for the full thickness, the full saturated thickness of the aquifer? And saturated thickness is typically abbreviated by the lowercase letter b. So if you take your hydraulic conductivity, your K, multiplied by b, there's your transmissivity. And so what it's showing is the difference between just what a unit window, if you will, of aquifer material would allow to pass through under a given gradient to what the entire column will be given, again, the same conditions where you've got a 1 by 1 gradient. So for any given gradient, the K times the B will give you your transmissivity, and it's an important variable. And it can usually be measured by pumping tests of some type or aquifer tests from slug testing and things of that nature. So if we can go on to the next one, Ann. Storativity, we've already touched on this a little bit. Unconfined, we have a specific yield. So we talked about that. This is what the aquifer will physically release from storage. And the graphic on the right, the upper portion of it shows an unconfined aquifer, and the water table has been lowered. The head, in this case, has been lowered by a unit decline. And you see the little cone at the bottom right where that much water has come out. So for a unit or a specific unit decline in head, this amount of water has come out. That's reflecting the specific yield. The water table has physically changed. The aquifer has been physically dewatered. In a confined or an artesian aquifer, the release of water is a result of lowering confining pressure. And you'll note, by the way, that the graphic here, it shows the potentiometric surface and it shows a confined aquifer, but it's not actually depicting a confining bed on the upper side. However, Just imagine that it's there, okay? And here the potentiometric surface, which is above the confining layer, that's not depicted here, but would be and should be, has been lowered. And so we've got a unit decline in head for this confined aquifer. The water is now released from storage, partially because of the compressibility of water. This water is going to be under pressure, and also because of just the weight of the overlying rock matrix, it can impact that as well. But notice the difference in the amount of water that's released. So you've got in the upper one where the specific yield is at work, quite a good, a full cone of water there as compared to just a tiny amount. And just to give you an idea of the range of things, in terms of percentages, typical specific yields can run from 5 to 25%, sometimes 30%. So a fair amount of release from the dewatering of that aquifer. In a confined aquifer, typical storage coefficients is what this is known as, are in the order of 1 times 10 to the minus 6 to 0.01%. So extremely small. You get a very reduced amount of water released from a confined aquifer as compared to an unconfined aquifer, because just the fact you're not actually physically dewatering that. We can move on to the next one. Anne has already touched on this a little bit. We have actually 4 different terms here. We've got isotropy and anisotropy, and then homogeneous and heterogeneous, or homogeneity and heterogeneity. So what this really refers to is how similar is your formation or your aquifer from one point to the next. Really what it's saying is that a homogeneous aquifer would be a situation when you have properties there, whether it's the grain size or it's hydraulic conductivity and transmissivity or whatever, are the same at every point in that particular aquifer, that particular formation. A heterogeneous one, on the other hand, is where they're different at every point. Maybe there's some areas where it's a little bit similar, but in general, it differs either vertically or laterally. So that column that's shown there in that photograph is some very different looking materials. You come up from conglomerates and gravels into more finer materials, and then some coarse sand at the top. That is a very heterogeneous deposit. And there's another aspect of this. It's called isotropy or anisotropy. In other words, the formation is either isotropic or anisotropic. That's a mouthful, that one. And it says that the properties are the same in every direction if it's isotropic, which is a lot like homogeneous, or it's different in different directions. And it doesn't have to be in all directions, but it's oftentimes a result of stratification during sedimentation, which is what you see in that really wonderful photograph that's there. And for another example here, if you look at the upper right graphic, it's a variation of the function of direction. Now, both of those are fairly isotropic in the vertical direction, but not so much in the lateral direction. The one on the left, it says isotropy, it's pretty much the same in all directions. There on the right, it is different going laterally. So this is something you're going to encounter in spades when you get into the karstic limestones, because of the solution features that we've talked about and really hammered on so far. You can see extreme levels of heterogeneity and anisotropy in karstic aquifers, and they can be really difficult when you're trying to characterize that aquifer and manage the use of that aquifer without getting into problems with the scale issues and things like that we'll be talking about more. And if we can go to the next one, and this is the last one of these, the hydraulic gradient and velocity. The hydraulic gradient we've already kind of looked at in the graphic that Anne had on the confined and unconfined aquifers cross section. It's just a change in head over a distance. So the hydraulic gradient is the change in head over change in length. And it's a fairly basic concept. And that's kind of what drives flow of water towards either a spring or a well, or else just general movement from water going, for instance, in the Korzal Basin towards the ocean. There's a gradient that's there. The velocity is simply the hydraulic conductivity times the gradient. And there's your velocity. So you can have a steep gradient or a very high hydraulic conductivity, you'll have a higher velocity if the material is homogeneous and the porosity is consistent. So in a flat gradient can also reflect both a high K and a high T, but not always. These things can play tricks on you, so it's really good to understand the relationships, but they are generally something that can boil down to a very simple concept. It's just sometimes difficult when you start mixing them together. You have to be careful about what you're talking about and keep them all in focus. Now, this is finishing up the slide deck. I do want to go to the last one here and just go through kind of what we've covered today, some conclusions. I love this beautiful graphic that Ann found. This is karst and, you know, sloping beds and the whole works in a very tropical setting. So what we've covered and why it's all important. We've looked at the basics, and perhaps some could say the very basics of geology and hydrogeology, the geology of Belize, the nature of the carbonate rocks and the karstic limestone. We've looked at how the Yucatan platform was formed, and then took a hard look at some of the characteristics of the aquifer itself. And we reviewed some of these important parameters that will be very important in your work in characterizing the Yucatan aquifer. And we're hoping that this introduction should provide you with a reasonable foundation for moving into the subjects that we're going to cover in webinars 2 and 3. In webinar 2, specifically, it'll be aquifer characterization. How do you put these tools to work? Water quality, water aquifer water balance, and then more detailed insights into the nature of karstic limestone hydrogeology, and an overview of the water resources of Northern Belize and integrated water resources management goals. So I encourage all of you who have an interest in what we've presented today to do some additional research and work on your own and look up any of these topics that may not seem quite so clear. I know on YouTube, there's tons of videos on some of the aquifer parameter type things that could be very helpful. And also the slide deck, of course, will be available in recording and through the unit itself. So thank you very much for your attention, and I'll turn this back to Ann. I think we'll kick it back to Elizabeth, if that's correct.
Thank you, Phil. That was so nicely done. And I think I'll just complete the thought with where we began in the beginning, and that is the geology of Belize is complex. It has everything to do with the understanding of the geology will help us to understand the groundwater. We know that there's plenty of rainfall, there's recharge in the aquifer, and that we know that there's certain challenges, and that is the extreme variability of rainfall that occurs as a result of, in particular, because of climate change. It exacerbates what is already natural variability and seasonal variability. And we also know that there is an added challenge for a coastal country in that sea level rise means saltwater intrusion. It means a loss of natural barriers and a change in that water quality balance. So with that, I am going to turn that over to Elizabeth, and we'll look forward to talking with you more as we get into the next webinar.
Thanks so much, Ann, and thanks so much, Phil, as well, for an absolutely information-packed presentation. I know that there was a lot in there for me, and I'm sure for many of you as well. Given the very limited time we have left in the window, I definitely don't want to run into the lunch hour for folks in Belize. I wanted to ask if there are any questions, and feel free to use the chat or unmute yourself. We can obviously also take questions back, provide email addresses, and answer questions in the interim between this session and the next session. So I will monitor the chat for a couple of minutes and see if we get any questions there. Any folks who would want to simply unmute yourself and ask questions, that's also welcome. I know we did say that we would do a sort of second exit survey. Given the limited time, I'm not sure if we would want to simply follow up with the survey results and perhaps the answer key for the survey following this session, and then we can start the second session with a brief discussion of these questions and sort of revisiting them. Does that sound reasonable?
That sounds very reasonable. Yeah, thank you for managing that, because we do want to stay within our time. And I think we got an idea of what those challenges of the poll presented as far as facets of the webinar. And I hope we have not overwhelmed you. It was absolutely information packed, and I'm so happy this has not only been recorded, but also the slide deck will be available for reference.
Yes, absolutely. And as I mentioned, our emails will be available. You have mine via the calendar invite for this session. If you were forwarded it or you don't happen to have it, Danielle has my email address, so you can feel free to connect with us that way. Otherwise, we're also obviously very close with the US Embassy, so feel free to reach out to us through those channels. Otherwise, seeing no questions in the chat and hearing no questions, I think we will go ahead and start to wrap up for today, and I will go ahead and end the recording. And I will say thank you so much to all of our participants for joining today and for taking the time out of your busy schedules to be here with us. And we hope that it was helpful and informative for you all. And we look forward to having you in our second and third sessions.